Nitrogen dioxide decomposes at a high temperature, and they've given us an equation. They've also shown us that it's an endothermic reaction, which we would expect for decomposition. A 0.317 mole sample of nitrogen dioxide is placed in a sealed flask and heated at a constant temperature until equilibrium is reached. At equilibrium, the flask contains 0.120 moles of oxygen. Calculate the mole fraction of each substance in the equilibrium. So the way I like to do these is to use a little method that you might have heard of. You may call it ICE, I call it RICE. I like to put the ratio down. So the ratio being 2 to 2 to 1. The initial amounts being 0.317 and no products at the start. And then writing down which one they've given me at equilibrium. The equilibrium moles of oxygen is 0.120. So we can fill in a change that this one went by 0.120. And what we need to remember is that the ratio and the change line are going to be in the same proportions. So 2 to 2 to 1 is the same as something to 0.12. So 0.24 is, if 1 is 0.12, then 2 is 0.24. And 2 is 0.24. And we remember that we subtract reactants and add products. And so our equilibrium moles will be, we'll use a calculator to work out 0.317 minus 0.240. That's coming out to be 0.077. And this one would be 0, add 2.4, which is 0.024. So that gives us a total equilibrium moles of 0.437. And so if we want to do our mole fractions, we take each of our moles and divide by the total moles. So this one becomes 0.176. 0.24 divided by 0.437 is 0.549. And 0.12 divided by 0.437 is 0.275. So we can write those answers on the answer line. One of the things that you can do to check your answers, if you add up the mole fractions, they should add up to 1, because fractions make a whole. So 0.275 add 0.549 add 0.176 on your calculator, and you do get the number 1. So that gives you a bit of reassurance that you've probably done that step right. The total pressure in the flask is 120 kilopascals. Calculate the partial pressure. So partial pressure is mole fraction times total pressure. So our mole fraction for NO2 was 0.176 times 120 on your calculator. 21.1 kilopascals. Table 1 shows the mole fractions of the three gases in a different equilibrium mixture. For this equilibrium mixture, Kp equals 59.7. Give an expression for Kp. So remember that equilibrium constants are products over reactants. This one's about pressures. So we want the partial pressure of NO, there's two of them, so NO times NO is NO squared, times the partial pressure of oxygen, divided by the partial pressure of NO2, and there's two of them, so NO2 times NO2 is NO2, partial pressure of NO2 squared. Use your expression and the data in the table to calculate the total pressure, so let's call that P. Okay, so this is going to be our total pressure in our equilibrium. Okay, so partial pressures, so like if we were to write down here, the partial pressures are, this would be 0.310 times the total pressure, this would be 0.460 times the total pressure, this would be 0.230 times the total pressure. So 59.7 equals 0.460 times the total pressure squared, 0.230 times the total pressure, divided by 0.310 times the total pressure squared. If we were to expand that, then we get 0.46 squared p squared times 0.230 times p divided by 0.31 squared times p squared, and we can see that some p squareds here cancel. So 59.7 equals 0.46 squared times 0.23 times p divided by 0.31 squared. So we'll be able to find p. So the 59.7 is staying where it was, and we're going to multiply up by 0.31 squared and then divide by 0.46 squared and 0.23. That leaves us with p on its own. So using our calculator, put those numbers in. And the calculator is giving me an answer of 117.88. I'm going to round that to 117.9 or 118. Either would probably be fine here. The equilibrium is compressed into a smaller volume. That means a higher pressure. Deduce the effect, if any, of this change on the equilibrium yield of oxygen. So when we have a higher pressure, we're going to shift to the side with the fewest moles to reduce that pressure. So let's have a look at the equation again. It went 2NO2. Let's go back to the top of the page. 2NO and O2. And its enthalpy change was positive. It was endothermic. So if we're going to reduce the volume, we increase the pressure, and we're going to shift to the side with the fewest moles, which is the left-hand side, so away from oxygen, so the yield of oxygen will decrease. But the only thing that could affect a Kp is temperature, so there would be no change to the value of Kp by changing the pressure. The equilibrium is allowed to reach at a lower temperature. When we lower the temperature, we shift in the exothermic direction to heat it back up again to oppose the change. So the first thing we need to write down is just to state what's given. Forward reaction is endothermic. That was because it had a positive number for its enthalpy change. When temp is lowered, equilibrium shifts left in the exothermic direction to oppose the decrease in temperature. And that is why we got less oxygen.